Okay, so in yesterday's class we continued our discussion on second order differential equations, and what we said was that earlier on we have seen the so-called Laplace transform methodology, which is very powerful, no doubt about that, but sometimes a simpler approach may be useful. And we started looking at some methodologies of looking at the differential equation solutions in some different framework. All right, so the equation that we start with is the same as what we always have, which is y double prime a1 y prime plus a naught is equal to a right hand side. And we said we'll start with the homogeneous equation first, which is b0 equal to 0. And like we had expressed earlier on, there are going to be two solutions, and we would take the linear combination of these two solutions and say that that's going to be the solution to the equation. And the two solutions are going to be coming about by saying that I'm going to assume y is going to be equal to e to the rt, and go ahead and plug it into the equation. You get a quadratic equation. You solve the quadratic, you get two roots, and each of these roots is going to give you one solution, and the solution to the homogeneous equation is c e to the r1t plus c e to the r2t. Okay. And if r1 and r2 are real distinct, there is no issue at all. You can just go ahead and take that as the solution. But if there are imaginary roots, then we said that we want to do something slightly different. And largely because many times these differential equations are going to be representing physical systems, and therefore having imaginary numbers in the solution is somewhat uncomfortable. If you are okay with it, it's fine, but it's somewhat uncomfortable. And I'm just giving you an example of a system that is modeled as a second order differential equation. If you don't understand that system, it's perfectly fine. But it's just simple motion of a spring mass damper system. And the final equation has been put in a particular form, and the form is not important either. But if you go ahead and look at the solution to that, then you see that there is an exponent, and in this exponent you have got a square root, and the zeta term in there can be greater than 1, equal to 1, or less than 1 in a physical system. And if it is less than 1, then you get imaginary roots, and it's customary to do this, and like somebody pointed out, it's not necessary that you do it. So the solution is going to be e to the power of m plus in, and you use the Euler identity to convert the exponential to the cosine and sine form. And we then say that we understand something about the linear combination of solutions being a solution, and therefore we just manipulate it a little bit and say that the solution is going to be in terms of the exponent and sines and cosines. And if there are repeated roots, we said that it poses a small problem, and the mathematicians have suggested the solution to that problem also. And what they do is to say that the solution is going to be the original solution multiplied by some kind of a function which is a priori not known. Go ahead and do a little bit of algebra, and we said that you're going to get that as coming out to be equal to the independent variable itself, and the solution therefore becomes e to the rt 1 plus c times the t, which is the independent variable. And we did a bunch of examples. We're going to look at a couple more examples today, so I'm not going to go through that. And then we said that there is this business of trying to see whether the two solutions are really independent or not. And we introduced this concept of a Wronskian. We never proved anything, we are just borrowing this. So the Wronskian is the determinant of the functions and their derivatives, and the functions are linearly independent if the Wronskian is not equal to 0. Okay. And there was a question at the end of class, so I've just added one more slide. Although this is not required because we have only two functions, and therefore the Wronskian is not really required in some sense, because you can just go ahead and look at those two solutions. One of the solutions was e to the rt, and e to the rt, if you expand it out, is going to be that. E to the r2t is that, and there is no way one of them can be obtained as a linear multiple of the other. Okay, but formally, if one looks at it, if you have got a large number of functions, which as of now we don't, but as we move along we will, but as of now we just say that if I have got a function which is going to be a linear combination of some other functions, C2, C3, C4, then it is linearly dependent. So F1 is a dependent solution, F2, F3, F4 are independent. F1 is linearly dependent on it because it's a, there are these multiples and it's a linear combination of the other functions. Okay. Now, in this particular case, we did not talk about this because the fact that you have only two functions and these two are fairly straightforward to see that one is not a linear multiple of the other. Okay. All right. So then we said that, okay, then why did I introduce the Wronskian? Okay, so it's some kind of a crazy thing that has been introduced. There's a reason for that. And so what we said was that if I know something about the Wronskian, then what I can say is that this Wronskian is the, if my governing equation is y double prime plus a1 y prime plus a naught is equal to 0, then this Wronskian, this some mathematician has very cleverly identified that the Wronskian is a solution to the first order differential equation, which is right up there. So if this be the case, what is the advantage? We will see in 1 minute. So we did some algebra, and what we said was that the Wronskian is going to be equal to this, and this we had defined yesterday. So you can take the derivative of the Wronskian, and the derivative of the Wronskian is going to be coming to be that. This also we had done yesterday. And now all that remains is for me to go ahead and say that the, let me see what happens in this particular differential equation. So I've got w prime, which is equal to y1 y2 double prime minus y2 y1 double prime. That's this guy here. And then a1 times w is going to be a1, and then the Wronskian is y1 y2 prime minus y2 y1 prime. Okay. And if I plug this guy inside here, you will get w prime therefore is going to be equal to y1 and then y2 double prime I'm going to get from here, which is minus of a1 y2 prime minus a naught. That's one of the terms. And then minus y2 and then minus a1 y1 prime minus a naught. Okay. So if I want to go ahead and plug these guys into here and then add up, then you'll see that it is identically equal to 0. Okay. So what you are saying is that after doing this algebra, we have shown that indeed the Wronskian is going to be equal to, or the Wronskian satisfies that differential equation. From a mathematician's point of view, it's not really a proof perhaps, but we are happy with saying that we are convinced that this equation is going to be satisfied when this guy W is the Wronskian. Okay. So if this guy satisfies this equation, then what's the solution therefore? Do I know the solution for this? Do I know the solution for a first order differential equation, right? Which is like so. What is the solution for this? We have seen this in the past. W equal to what? We had talked about the integrating factor, right? So we said that there is something called an integrating factor, which is going to be e to the power of integral a1 dt multiply throughout, and then that's going to give you d dt of e to the power integral of that. So this guy becomes minus of integral of a1 dt. That's the solution to the first order differential equation. Okay. So this is something we have seen earlier on, and if this is correct, then what's the advantage that I'm getting? The advantage I'm getting is that this guy is known to me, so I can evaluate this, and let me just say that I'm going to keep this constant as 1 because later on anyway I'm going to have to evaluate that constant. So if I take this constant equal to 1, then this is y1 y2 prime minus y2 y1 prime. Okay. Okay, what's the big deal? Okay. The big deal is that if one of the solutions is known, the second solution is known. Okay, that's what this whole Abel's theorem is all about. Okay, which is that if I'm going to say that one of these solutions is known, then I can use this formulation to get the other solution. Okay, so if let us say one of these solutions is known, the other solution I'm going to be able to easily evaluate by looking at that equation there. Okay. Again, you can ask what's the big deal, because I have already gotten that equation and I solved that. Okay, so what will happen is that as we move along, perhaps in the next class, we are going to see that there are some second order differential equations for whom getting one solution is not a big deal. The second solution is something which you are going to have a lot of trouble to get, and then you use this Abel's theorem to go ahead and get the solution. Okay, so what this business is telling me is that I know what the Wronskian is, I can evaluate what the Wronskian is because I know the Abel's theorem and the governing equation, and if one of the solutions is known to me, I can go ahead and get the second solution. Okay, so we'll use this later on. So this is just to keep in mind, because we were looking at the independence or the linear independence of the solutions, and then we introduced Wronskian, and therefore we go ahead and looked at this, and we're going to use this Abel's theorem once we are done with some more straightforward stuff. Okay. All right, so now let's go ahead and say that we had looked at the second order equation, and the second order equation, when the second order equation is a homogeneous equation, we said that we got the solution as some exponential or some sines and cosines. Now if the equation is non-homogeneous, then how does one go ahead and tackle it? Okay. So once again we take the first order equation as the vehicle, and then the procedure is a general procedure. Okay. So there is a right hand side which is, let us say, some random function. To start with, let us say that it is a polynomial. Okay. And just to illustrate the method, we are going to say that this polynomial, let it be some g1 times t square. So this is some g1 times t square. Okay. And this is the so-called method of undetermined coefficients. And so this is the method of undetermined coefficients, which means that we are going to come up with certain coefficients which we are going to determine. Okay. To start with, we don't know, they are undetermined. We are supposed to determine these so-called coefficients. So what we say is that this is the right hand side, and I hypothesize that my particular integral y is going to be equal to g1 hat times t square. This notation is crazy, but somehow I have used it. g2t plus g3 hat. Okay. So the right hand side is a g which is an unknown, and these g's with the hats on them are those so-called undetermined coefficients which we are trying to evaluate. Alright, so what's there to do? Fairly straightforward. Go ahead and substitute. So we go ahead and substitute this guy, and we have our equation, and you have y prime. So y prime, so we are hypothesizing that this y, which is the so-called particular integral, is the solution to the governing equation, and therefore this guy is g1 hat times twice t, I'm just taking the differential, that's all, plus g2 hat. Okay. So twice g1 hat t plus g2 hat, this is the first term, which is the y1 prime term, plus then I have got this y which is equal to the g1 hat t square plus g2 hat t plus g3 hat, and the sum of these two guys is equal to 0. So y1 prime, which was the original equation, plus a naught times y plus a naught times this. So therefore if I plug that y particular in there, I just get this plus this is equal to 0, and that's what you see on the right hand side. Sorry, this plus this is equal to g1 t square. So all that we have said is, you have hypothesized there is a polynomial on the right hand side, and what you are supposed to do, or what is suggested that you do, is to take that the highest degree of the polynomial and take all the lower degrees. All the lower degrees have to be taken. So you take, if g1 t square is that guy, then you take some g1 hat t square, g2t plus g3. If it was g1 t cube, then you would take g1 hat t cube and then downstream. Okay. So take the polynomial and take all the lower orders or the lower powers of the polynomial, equate it to 0, and then what should we do? Left hand side is right hand side, right? And therefore what can you do, or what can you say about the coefficients? So the power of the coefficients or the power of the variable must be equal to same on both sides, and therefore we just take the coefficient. What's the coefficient of t square here? What is the coefficient of t square? A0 g1 hat, correct? That is A0 g1 hat t square is equal to g1 t square, okay? And the coefficients on t square have to be the same, and therefore I get what is going to be my g1 hat, right? I was trying to determine what these hats are, okay? So g1 hat is going to be, so g1 hat is going to be g1 by a0. So I know what my g1 hat is now. This is that. And what would I do next? What would be the next step now? Equate the coefficients of t and the constant terms, and then you will get those equations and go ahead and get the other coefficients, okay? So what we are just now saying is that if you have a right hand side which is going to be some kind of, I have got a differential equation, and if my differential equation is this was we had said a naught y1 prime plus a naught y is equal to the right hand side. Now you don't need this guy here. Whatever is there in here, whatever is that linear operator in here, this is going to be operating on y is going to be equal to this, and this is a polynomial, and if the polynomial is equal to t square, then you have got these undetermined coefficients which are these g1 hat, g2 hat and g3 hat. Okay. So you get g1 hat, g2 hat and g3 hat. Okay. So that's what we have basically done. Okay. Even though we have said that this is the first order differential equation, it need not be, it can be any order differential equation. The methodology remains the same. Okay. Now, it's always not going to be a polynomial on the right hand side. It could be several different variants there on the right hand side. So if the right hand side happens to be some kind of, there is this equation here, and this is g1 e to the power of g2t, right? Then the suggestion that is being given is that you use the particular form which is going to be g1 hat e to the g2t, plug it in, and then you are going to be getting one equation and you are going to get a solution for this so-called g1 hat. Okay. And okay, now suppose the right hand side is, g1 cos g2t plus g3 sin g4t. Now in this particular business, everything is, there is a right hand side, somebody is suggesting what you are going to be using as the solution to the equation. Okay. So the particular solution here, you are going to guess it once again as y particular integral is equal to a g1 hat cosine of g2t plus a g2 or g11 hat cosine of g2 sine of g2t plus g2 hat cosine of G3t, G4t plus G21 hat, G31 and sine of G4t. Okay. All that I'm trying to emphasize here is that when you have got a right hand side which is a cosine or a sine, then you are going to have all these terms that are going to be there. Okay. So you're going to put all these terms and then you are going to just go ahead and brute force substitute in the equation and then equate the left hand coefficients with the right hand coefficients. That's about all the procedure is. Okay. So put everybody else, some of them may come out to be 0, that's another issue altogether. So if your right hand side has got either a cosine or a sine, right, the particular integral is likely to have both sines and cosines. That's the message that is coming out from here. Okay. And if more than one are there, then more than one are there. If another one is there, you have another one, and so on and so forth. Okay. So if you had a polynomial of order n, then you said that you take everybody downstream of n. That is the suggestion. Okay. And if you have got a sine or a cosine, then you take sines and cosines for each of these terms. Okay. If you have an exponential, then you take the exponential. Okay. So basically what we are saying is that you're going to guess the form of the solution to be the same as what is there on the right hand side. Okay. So there's something on the right hand side. You hope that the particular integral is going to be something that is going to be related to the right hand side. Plug it in and then just brute force algebra is happening. Okay. Now what happens if the right hand side is the solution to the homogeneous part? Okay. So we have seen that if you are talking about a y double prime plus a1y prime plus a naught y equal to some right hand side equal to 0, if the a naught and a1 were given to you, and let us say you got some kind of an e to the power of r1t and c1 e to the r1t, c2 e to the r2t, and the right hand side had e to the power of r1t. Okay. So then you can't just take that because that's anyway going to satisfy it, right? So it's not going to give you the particular integral, right? What happens if I just plug this in? Remember, we said that you have the right hand side, you hypothesize that the particular integral is going to be similar to the right hand side. Okay, so this is the solution, and so I hypothesize this is what is the particular integral. I hypothesize that this is the solution. Then what's going to happen? What will happen? Yeah, because C1 equal to 1. See, what will happen is that this will satisfy this, right? Because this has come from this. So when you plug this guy inside here, you will get this as 0. So you can't evaluate whatever is your C. Okay. So you will not be able to evaluate what this C is, and therefore the suggestion is that you multiply it with the independent variable. So if you have got e to the power of r1t, for example, you will hypothesize that the particular integral is some t c e to the r1t. Okay. And then hope that it works. If that does not work, then you multiply by t square and so on and so forth. Okay, so we have seen a couple of things. This is a table that I have picked up from your textbook. these are certain suggestions. Okay, we have a method of undetermined coefficients, so to speak. So we need some kind of a hypothesis for the particular integral. You go ahead and make certain approximations, and if your function happens to be what is there on the right hand side, here is the suggestion on the left, my apologies, if whatever is the function on the right hand side is on the left hand side of that table, then you are going to use the suggestion that is given on the right hand side of that table. Okay. Alright, so that's the so-called method of undetermined coefficients. It appears to be clumsy as of now, but sometimes it's very handy because you just can look at the right hand side and very quickly get what the particular integral is. Okay. Alright, it's just basically going ahead and using a suggestion which somebody is giving. Go ahead and use it, plug it in and get the so-called undetermined coefficients. And every function under the sun is not given in that table. If it is not there, you can make some intelligent guess. If it works, it works. If it doesn't work, then you have to do something else. Okay, and that's what's a much more powerful methodology, which is called the variation of parameters. So the recommendation is to go ahead and try to use the method of undetermined coefficients. If it doesn't work, then you go to a slightly more powerful method, but it's slightly more messy also. But this guy will work. Okay, so what's the concept here? Once again, remember that our objective is all the time to get what the particular integral is. Okay, we have now already established that we have a non-homogeneous equation, and if the non-homogeneity is there, then there is going to be a homogeneous solution, which we already have seen how to get. The particular solution is the one which gives trouble, and we are trying to establish what that is. And here the hypothesis is very similar to what we had in the past. We have done this in the past once, which is what you say is that the solution or the particular integral is related to the homogeneous solutions in a linear fashion. Okay, so what you say is that if y1 and y2 are solutions to the homogeneous equation, then the particular integral is going to be behaving like so. So the particular integral is going to be this guy plus this guy, and you need to figure out, however, what this u and t is. It's not straightforward to do just by inspection. You need to do a little more work to get what these guys are. Okay. Now what's that work? What is that work? Substitute, that's all, right? Brute force, everything is brute force, nothing very profound is going on. Just brute force substitute and then hope that it works. Okay. Alright, so I've got y particular integral, I'm hypothesizing is uy1 plus vy2. Okay, my governing equation is going to have let us say some kind of differentials. So let us differentiate this guy. Okay. So y prime is going to be u prime y1 plus u y1 prime plus v prime y2 plus v y2 prime. Okay, that's my first differential. Okay, now what we say is I need also my second differential, right? So what these mathematicians have done, they're very smart people. So what they said was that I don't want to deal with the second derivative of this guy here. Okay, so I don't like to deal with the second derivative. So let me get rid of the first derivative itself. Before I take the second derivative, I get rid of the first derivative. How do I do that? How can I get rid of this first derivative here? This guy is first derivative, this guy is first derivative. So again I hypothesize something. Okay. At the end of the day, maybe it will work, maybe it will not work, but you can always hypothesize certain things. So you say that u prime y1 plus v prime y2, I'm going to hypothesize is equal to 0. The method is not complete and therefore it's perfectly fine to do that. Okay. So we hypothesize that and get rid of these two terms. Okay. So what have we done? We have said that my particular integral is going to be some unknown parameter u times one of the solutions plus v times the other solution. Okay. And then we say that if you plug this guy into the original equation, it should work, and it should. And you started doing that, and then you said that no, this is giving me too much work to do, so let me just get rid of a couple of terms. Okay, that's very smart of these guys to do. Okay, so now I take the next derivative, which is again u prime y1 double prime plus u prime y1 prime plus v prime y2 double prime plus v prime y2. Okay. V prime y2 prime. Okay. So that's my second derivative. So y double prime is equal to this and y prime is equal to this. So now all that we need to do is to substitute in the original differential equation. What was my original differential equation? My original differential equation was this guy multiplied by 1 and this guy multiplied by a1, right? a1 times y prime, a plus y double prime plus a naught times y, and y is nothing but our original, which is u y1 plus v y2. Okay. My original differential equation is y double prime plus a1 y prime plus a naught equal to 0. So this is my original differential equation equal to an RHS, and I'm trying to find a solution to this, and I am hypothesizing that the ypi is uy plus vy2, uy1 plus vy2, and this right hand side is, let's call it g. So we have everything we need. We say a1 times the first derivative, then second derivative plus a naught times that function there. Okay, and remember this guy is still there. This guy is still there. We can't forget that guy. That guy has to be given due respect, so it is still there. Okay, now you just go ahead and do a little bit of algebra and go ahead and group the terms, and what you get is you're going to take u times, if you take u common, so you can now go ahead and take my u common. This algebra I'll just not attempt to do, and then v you're going to take common. And what you get is the equation itself, plus a1 y1 prime plus a naught y2 plus a1 y2 plus a naught plus u prime y1 prime plus v prime y2 prime is equal to g of t. Okay. So if you do the algebra correctly, which hopefully it is right there, so you just take this, rearrange the terms, and you're going to get u times this plus v times this plus this is equal to this. And what is this here? What is this? What is this guy here? This is 0. Why? Because y1 is the solution to the homogeneous part of the equation. The equation itself is y double prime plus a1 y prime plus a naught y is equal to gt, and the homogeneous part is if I'm going to take this equal to 0. So this guy is gone. Similarly, this guy is also gone. Okay, so what remains is this guy here. So what remains is this guy here. Is this equation enough? Now I have done everything I can do. Okay, we have just taken the hypotheses, we plugged it in, we did everything, and then we now come up with this equation here. How to solve this? How to solve this? Can we solve this now? So this guy here who is standing there in that box, okay, that has to be given due respect now. Okay, so I've got this equation here, and then I pull that guy down here, which is u prime y1 plus v prime y2 is equal to 0. So now I have got two equations in two unknowns. Okay, what are my unknowns? U prime and v prime, or u and v, whichever way you want to look at it. So I've got two equations in two unknowns. I can go ahead and get the solution. What am I looking for? I'm looking for u and v, and u prime and v prime I have just established. So I can just go ahead and integrate these guys and get the solution. Okay. So u and v, so this is a sure shot methodology. Okay. So in the undetermined coefficients, we needed a suggestion. Somebody had to give us a suggestion. Some smart person has to give us a suggestion. We can use the suggestion, brute force, go ahead and plug it in and get the coefficients. In this particular case, that equally smart person has suggested something, but what that person has suggested is coming down to the solution of a differential equation. Okay. So you need to be able to integrate that. Okay. I have anyway permitted you to use these online tools, so if it's a messy integration, you can just go ahead and very easily get the solution to that integral. Okay. So you can go ahead and get what u is and what v is. Okay. So that's going to be the so-called variation of parameters. Okay. We'll look at one last case. So all of what we have done so far has been where the coefficients were constants. Okay, now let us relax that. So we had y double prime plus a naught y plus a1 y prime plus a naught equal to a right hand side, and this guy were constants. Although we have not explicitly been saying that, now we say that a1 and a0 were constants. Okay. And now we relax that. Okay. And we are going to slowly relax that. So first what we do is we take a very special case, which is the so-called Euler-Cauchy equation. Okay. And this guy is x square y double prime plus x y prime. This is the standard form of the Euler-Cauchy equation. So remember now that there is somebody who is depending on the independent variable, which is multiplying the dependent variable or its derivative. So I've got x square, it could be t square. So it could be x square, it could be t square y double prime plus ty prime minus y equal to 0. That's perfectly fine. And this has the special name and has therefore a special solution. We'll look at a general solutions maybe later today or early next class. Okay. So the special solution, just like what we did, was somebody has to give us a suggestion. Okay. And the suggestion is you attempt C x to the power of r. Okay. So where r is the root. So you have this equation. You are trying to say that I'm going to attempt this and hope that things are going to work out. And this guy here now, I have got x square. What is y double prime? What is y prime? Y prime equal to CR x to the r minus 1. What is x double prime? CR r minus 1 xr minus 2. So you plug those guys in here. X square CR r minus 1 x to the r minus 2 plus x times CR x to the r minus 1 minus y is equal to, and y is C x to the r equal to 0. So we are going to now divide through by x to the power r. Okay, we'll just divide through by x to the r. Hope that that's not equal to 0. If it is equal to 0, we are going to look that as a special case later on. As of now, let us just say that x to the r is not 0. And if you do that, this is x square, this is x to the r minus 2. So I've got an xr there. This is x, this is r minus 1. I've got another xr here. I've got an xr there. Okay. So everybody has got an xr. So this is sometimes also called an equidimensional equation. So all these x's have got the same exponents in some sense. Okay. So this guy now is going to be r into r minus 1 plus r minus c equal to 0 minus 1. And this is another quadratic which you can go ahead and solve, get the solution for r. Okay, now what happens if again we have got the same cases which we had, which is if the roots are real distinct, then this is fine. If the roots are not real and distinct, then what does one do? If they are imaginary, then okay. So if the roots are imaginary, that's just some kind of an extension of what we had done in the past. So what we need to realize is that x to the power r, x to the power r is e to the power of what? R log x ln x r. Okay. So and then now you say that I'm going to use this guy here, and if the roots are complex, suppose I have got a plus ib as my roots. Okay. Why are we obsessed with this e to the power? Why am I wanting to put this in the e to the power form? So that you can write it up in terms of sines and cosines. Okay. Because we have said in the past that e to the power of I theta is cos theta plus I sin theta. Okay, so I would like to write it in terms of cosines and sines, and you can go ahead and see the same thing that we did in the past. Okay, I don't want to do that again now. So you can go ahead and do the same methodology, and you are going to get y is going to be x to the power a c1b log x plus c2 sine b log x. Similarly, if you are going to have equal roots, then, or the repeated roots, then you can go ahead and use the same procedure that we had done in the past and show that this is going to be equal to this. So this is going to come to you as your home assignment in the next one. Okay, so you're going to do that on your own, and you're going to just say that I'm going to have, if the roots are distinct, then we have done up to this point. And if the roots are imaginary, you will go ahead and do that little algebra and show that the roots are going to be that, the solution is going to be that. And if the roots are going to be repeated, you're going to show that that's going to be that. Okay. All right. So let's just look at a couple of examples before we say that we are going to be leaving this business of second order differential equations with constant coefficients. Okay, so I've got an example, y double prime minus twice y prime minus 8y is 10 e to the minus x plus 8 e to the 2x. Okay. So the homogeneous part is going to be equal to 0. That's going to give me the homogeneous part. And what would be the homogeneous solution? I would get r square minus twice r minus 8 equal to 0. Okay, so this will give me r minus 2, r plus 4, r minus 4, r plus 2, and equal to 0, and that's going to be giving me the roots of this equation. Okay. That we have done enough number of times. So the solution to my homogeneous part is going to be c1 e to the minus 2x plus c2 e to the 4x. Okay, so that's coming from here. Now what about the non-homogeneous part? Let us say that we are going to use the method of undetermined coefficients. So what should I guess my particular integral to be? What should be my particular integral? Okay. What we have said is, you try to guess the same thing that is there on the right hand side. Okay. So my right hand side is this here. Okay. And a word of caution was that these exponents should not be the same as what you had. So e to the power of 4x and e to the power of x, 2x. Okay. So this was my homogeneous solution. My homogeneous solution had c1 plus c2. So c1 e to the minus 2x plus c2 e to the 4x. Okay, so that was the solution to the homogeneous part. And this guy and this guy are not the same as this guy and this guy, right? So you attempt the solution and say that my particular integral is going to be equal to some undetermined coefficient c or a e to the minus x plus b e to the 2x. So this is the guess that you start with. Okay. So my right hand side is e to the minus x, e to the 2x, and therefore that is not part of the homogeneous solution that has been obtained, and therefore I guess my particular solution to be similar in form here. Okay, and then I do the algebra. Okay, so the algebra is all given here. You can go ahead and look at the algebra, and you do some amount of algebra, and you are going to get what your coefficients are. Okay, and then you can go ahead and get the solution itself. Okay, So let's just, okay, we stop here today. I'll see you again on Thursday. Thank you very much.